This video lesson is about triangle similarity and specifically proving triangles are similar by using the angle-angle theorem, or AA. So we're going to be doing some proofs and some things. We're going to be building upon dilations and similar figures. So let's just review really quickly. If we have a triangle XYZ, here's our triangle XYZ, the smaller one up here, and that is transformed by a dilation centered at the origin, and this is our scale factor of 3. We want to know what the side length of xy is. So this is the side we're trying to find. What is xy? Well, we're given that x prime y prime is equal to 9. So we're saying that xy, or x prime y prime, is equal to the scale factor of 3 times xy. So if we know x prime y prime is 9, that equals 3 times xy. So if we divide by 3, then we know that xy is equal to 3, which makes sense because this is a smaller figure, and if we take 3 times 3, that's going to give our dilated image of 9. So we need to remember that. Now, if we're going to map similar figures, when we map similar figures, we're saying we're taking a figure and we're going to do a transformation on it. So, and there can be a sequence of transformations. Sometimes it's just a dilation, which was this example right here. We just dilated this. Sometimes we're going to make it larger or smaller, and then we're going to move it in one of 3 ways. We can either translate it, which just means that slides it. So if you have a triangle like this, you can slide it and it's the same thing. You can slide it and it's the same thing. Those are all translations where the orientation is going to remain the same. If we rotate it, a rotation means if I have a triangle that looks like this and I rotate it, then my new triangle is going to look something like that. So the orientation is no longer the same. If these 2 angles were congruent and these 2 angles are congruent, they have been rotated, so they're not in the same, they're in a different orientation. The other thing we can do is we can reflect it. And reflect it is if you have a line, and I'm going to draw a right triangle so maybe we can see this clearly. If you reflect it, that means you're reflecting each point across like a mirror image. And so that is a reflection. So the orientation is just reflected or opposite. So this is a reflection. That's like a mirror image. And this is a rotation where it's rotated around something. So you can have a dilation and a rotation, and you can have all of these combined. But what we do when we look at this, what is the sequence that could map A, B, C to X, Y, Z? Now you'll notice if I look at this, I say, well, I know XYZ is smaller, so if they're not the same size, so it's smaller or larger, that tells me we have at least one dilation. So we have a dilation. The next thing that we need to see is if it's in the same spot, if it's moved at all. Well, the orientation looks that we've just slid it. We haven't rotated or reflected it. And so we have, in this case, we're going to have a dilation and a translation. And we know it's a dilation by 1/4 because if we take the ratio of the sides, we take the new image, and we'll just do the one with 1 and 4, xz over ac, that's 1/4. And if you did that 1.25 over 5 or 1.5 over 6, it would have the same proportion. So that's the type of transformations and the sequence. So first we dilated it by 1/4 and then translated it over. So if we take a look at this one, this is something you might want to write in your notes. So pause the video if you need to and take note of this. So you'll notice that a similarity transformation is one that preserves angle measures. So dilations preserve angle measures because when we make them bigger or smaller, the angles stay the same. Like L is still congruent to L prime, N prime and N are still right angles, and so forth. Rigid transformations, they preserve angle measures. Those are what we're calling translation, reflection, and rotation, meaning we're not changing the size of any of the things, we're just sliding them, reflecting them, or rotating them. Or the compositions of those. So if you have a combination of these, you can do that. So 2 figures are similar if and only if there is a similarity transformation. That means these are similar if we can identify a transformation that makes it so. So let's use this to determine similarity. So which steps would you make to determine these figures are similar? Now notice this is A double prime, B double prime, and so forth. That means we're going to have multiple transformations. So in this case, I can see that DC is my longest and D prime C prime is my longest, and it's on the top of this, my pre-image, but in my image or my translated one or my transformed one, it's not. So I can tell right away that there is some kind of a reflection that took place. So I know that there's a reflection somewhere. I also see that this is smaller than this one. So I know that there is a scale factor of less than 1. So I'm going to say there's a scale factor of less than 1 that's happening. And so then let's take a look. Is there a scale factor of 2? Well, no, there's not a scale factor of 2 because we're making it smaller. So that one is not true. Let's check this 1/2. The way I'm going to check the 1/2 is because the sides are going to be proportional as well. So DC, I can see is 1, 2, 3 units. And then my original DC was 1, 2, 3, 4, 5, 6 units, which reduces to 1/2. So I know my scale factor is going to be 1/2. So we could multiply the vertices of this polygon to get a smaller image. Then would we translate it? Well, we don't have a translation. Remember, we have a reflection. And so this is the only other one that would make sense, because if we perform 2 different dilations, those would not be 1/2, which we do have. So we reflected it and we dilated it. So here is the angle-angle similarity theorem. It says if 2 angles of one triangle are congruent to 2 angles of another triangle, the triangles are similar. So if all I have to have is 2 angles. And I'm going to make this one smaller, sorry. Let's do this again. So then if I have another triangle right here, and I know that those 2 angles are congruent, then I can say that those triangles are similar to each other. So why do we only need 2 angles? Well, because if you add 3 angles of a triangle, they always have to be 180 degrees. So if this is 90 and this is 50 and this is 90 and this is 50, those both have to be 40. So all 3 angles are similar. So that's one of the reasons. But if you can get 2 angles of a triangle congruent to 2 angles of another triangle, then we know they are similar. So let's use this. Which diagram could use to prove this using similarity transformations? In other words, how can we know which one of these shows 2 angles congruent to another? Well, let's take a look at this third one right here. We have A is congruent to C and E is congruent to C, but those don't mean they're necessarily congruent to each other. So that is not true. In this case, we have A is congruent to E, but we don't have any other angles marked, and we don't have parallel lines or vertical angles to prove any others are congruent. So we can't do that. If we look at this first one though, we have A is congruent to E, and we know that angles C, ACB, and DCE are vertical angles. And we know vertical angles are congruent. So we know that we have 2 angles of the triangle, so we know that those ABC is congruent to EDC. So let's walk through this. This was in your the instruction, but I just wanted to walk through and kind of help you out with this. So the first thing we want to take a look at is the first one are given. We're given that the lines are perpendicular. QR is perpendicular to PT, and we're given that QPR and STR are congruent. So we have 1 angle. We just need to get another angle. So the next thing we want to look at is we know because these are perpendicular, what do we know about SRT and QRT? Well, we know that they are right angles. And the reason we know that is because they're perpendicular. So we know they're perpendicular, and now we can say they're right angles. Well, what do you know about right angles? Well, we know that right angles are congruent to each other because all right angles are congruent. So that's the next step. Now we know that we have QRT is congruent to SRT, and now I have 2 angles in 2 triangles that are congruent. So now I can say that the triangles are congruent, and the reason is because of the angle-angle similarity theorem. All right, this is another proof with different angles that we're going to be using. This time we have parallel lines. We've got 2 lines marked as parallel, right here, and we have a right angle. Notice this right angle is part of the smaller triangle, and it's part of the larger triangle. So we know that NM is parallel to XZ, because that is given to us. So NM is parallel to XZ. That's our given. So if we consider NY as the transversal for this, then what do we know about angle N and angle X right there? Well, we know that corresponding angles are congruent. So using the corresponding angles theorem, we can state that XY or YXZ is congruent to YNM. And then because we know XYZ is congruent to NYM, even though this is the same angle, it's a different name in each triangle. So this angle is XYZ, and it's also angle NYM. So we know that those are congruent because they're by the reflexive property, meaning an angle is congruent to itself. Therefore, NYM is similar to triangle XYZ by angle-angle similarity theorem. So again, we have two angles. This one is the same angle, but by reflexive property, it's in both of those triangles. And with our parallel lines, we can prove those. So let's practice here. If these two triangles are similar, what happened? What happened to get from ABC? This one is called our preimage, and this is the transformation triangle. What did we have to do to get from here to here? Well, it looks like it's a different size, right? So we know we have to have a dilation. So that's going to give us one of these. It's either going to be a dilation and reflection or a dilation and translation. Well, how do you know which one? Well, if the orientation is the same, so in other words, it goes ACB and ACB, then that is going to be a translation. A reflection, it would be opposite. It would look like that, and bigger. So that's a dilation and a translation. All right, take a pause the video and see if you can do this one. Now be careful because you've got a composition of functions. You have two different things being applied to create a new triangle. So try this one out. Okay, I want to walk you through this transformation because there's two compositions and we always start with the one on the right. So the first thing we did is we took LMN and we multiplied by a scale factor of 2. So each vertex we multiplied. So this would be -1, 2 would become -2, 4. And that's our green triangle. That was the first transformation. That became L prime. Then we took 0.75 to get L double prime. And so 4 times 0.75 was 3, and so this is -1.5 and 3, -1.5, -1.5, and 3, -1.5. So this pink triangle is our final one that our questions are being answered on. Now, are those angles congruent? Well, yes. Transformations and dilations preserve angle measure. They're still right angles, so those are congruent. Are the triangles similar? Yes. We just dilated them. That maintains similarity. Then we have to look at, are they congruent? That means, are they the same lengths? Well, no, our original triangle is smaller than our dilated triangle right here. And then we look at the coordinates. And the way we could get these coordinates without plotting them is I could take my original coordinates. L is equal to -1, 2. M is equal to -1, 1. And N is equal to 2, -1. And all I would have to do is multiply each coordinate first by 2 and then by 0.75. So -1 times 2 times 0.75. That gives me -2 times 0.75, which is equal to -1.5. And if we look at L, that says positive 1.5. So we know that's not true because I need a negative. And you could do that with all of them, and you would find out that the vertex of N double prime is correct, but the other two are not. So let's prove a triangle similarity. See if you can do this one on your own and then come back and check. Okay, you're asked to fill in the missing parts. This part where it says F, H, G, and G, J, K are congruent because they are right angles, so we know all right angles are congruent. So that's how we know they're congruent. Then we're labeling F, G, H, I wrote them backwards, and K, G, J are vertical angles, so we know that those two angles are congruent by the vertical angles theorem. And now we have two angles. So we have the angle-angle theorem of similarity. Okay, try this one. All right, because we have two parallel lines cut by transversal, we know that angle YXV and WZV right here and right here are alternate interior angles. We know they are congruent. We know that right here we have vertical angles, so these triangles are similar by the angle-angle similarity theorem.